Hi, good morning guys. In today's class, we're going to discuss about one-way authentication and mutual authentication. So in one-way authentication, it's of two. One is password-based authentication and second one is certificate-based authentication. So in mutual authentication is of four. One is shared secret-based authentication, asymmetric key-based authentication, authentication and key agreement. Fourth one is use of timestamp. So in that, first we're going to see what do you mean by one-way authentication. So in one-way authentication, a client and server communicates will going to happen. In that, the client has to authenticate itself to the server. So here, the server may or may not be authenticated to the client. So this is referred to as one-way authentication. So in this one-way authentication, first we're going to see the password-based authentication. So here in this password based authentication, as we guys know, we will be logging into your Facebook, Gmail account, etc., by giving your username and the password. So that is what the password based authentication is. In that, first we're going to see communicating password. So in that, first we're going to give the login name and we're going to give password. So the login name can be anything. Here I have given it as alpha and password I have given it as XA exclamatory 2BZ. So by the client will going to give the login name and the password, and here the server will going to authenticate. It will going to check for the username and the password. If the username and the password matches, then it will be said to be unauthenticated. So this is what it is. So now here in this, there is a true drawback associated with it. So the first, the password is sent in clear. So an attacker can eavesdrop on the message containing the password and later impersonate the real user. So the second one is the password are stored in unencrypted form in a file on the server. If an internal attacker obtains access to the file, all the passwords stored on the server could get compromised. So in order to avoid this, we're going to use cryptographic hash of the password. So that is what it is, communicating hash password. So here the same concept we're going to use, but the whatever the password we're going to give, it will be hashed. What do you mean by hash? Whatever the input we're going to give, it will be hashed and it will going to give it the output in the form of a digest. So whatever the real password is, it will be converted into an hash password or to a digest, and that will be sent into a server. So here the server will going to check for the username and the hash of the password. If this matches, then it says that it has been authenticated. So, however, an attacker could snoop the information about a user and the password, and hence the server will going to give the username and the hash of the password. So which will be called as a replay attack. So in order to avoid this, we have four ways of preventing this replay attack. So here the first one is A will be acting as a client and B will be acting as a server. Suppose assume it as. So now what A will going to do? A will going to communicate its identity A to B. What the B will going to do? B will going to send its nonce R. This is capital R. So nonce is a random number which has been generated freshly, and once this nonce is used, cannot be reused again. So once the nonce has been used, it cannot be reused. The size of this nonce will be of 256 bit. So now what the B will going to do? B will going to send its non to A. So now what A will going to do? A will going to perform some function on this, and it will going to do do a password and R with this function f. So now what this b will going to do, the b diagram will going to do, here a will going to communicate its identity a to b. Again here b will going to send its nonce r is a freshly generated a random number, so it will be sent into an a. So here what a will going to do, a will going to perform a cryptographic hash on it, and it will going to concatenate both the password and the nonce r. So this is what it is, it will going to perform an hash function, that is h here, and it will going to concatenate both the password and the nonce which is generated. So in third, what it will going to do, here A will going to identify its identity as A to B. So what B will going to do, B will going to send its nonce R, that is a randomly generated number R, to A. So what A will going to do? A will going to encrypt the password by of R, encrypt the password of a nonce. So here encryption will going to takes place. What about this in D? What is A will going to do? A will going to send its identity A to B. So here B will going to encrypt this nonce by using a PW, that's password. So now what A will going to do? A will going to decrypt this nonce R by using a decryption key, and it will going to check the nonce R to B. Here whatever the B has sent a nonce and whatever the A is sending to nonce B after decrypting, if it matches, then the communication passes. So next we will going to see mutual authentication. What do you mean by a mutual authentication? So it's an often necessary for both communicating parties to authenticate themselves to each other. For example, in internet banking, you need to authenticate yourself to a bank, and bank also should authenticate themselves to you. That is what the mutual authentication is. So here we will going to see the first one is a shared secret based authentication. So here a straightforward extension protocol of for one-way authentication is shown in this. So this is a straightforward one, which is a flawed protocol, and the how this flaws will be done on the based on this attack will be showed in this figure, and this is the corrected protocol of shared secret based authentication. So here what this will going to do, here in message 1, so A will going to send its identity A in the form of nonce R of A. So this is A's nonce which has been sent into B. So now in message 2, what B will going to do, B will going to respond to the challenge by encrypting RA. So here encrypting RA with the common secret key K that A and B share. B also sends its own challenge RB to A. So A, what A will going to do, A will going to respond to B challenge in a third message here. In third message, that is third message appears to complete the protocol for mutual authentication, while the protocol may appear a valid one. So in this, what one attack will going to do, so here the attack, what it will going to show is in message 1, an attacker C, so this C is an attacker, so the attacker C sends a message to B containing a nonce RA and claiming it to be A. So in message 2, B, what it will going to do, B responds to the challenge with encryption key of RA with a key K and its own challenge RB as required by the above protocol. So in message 1, now C attempts to connect to A claiming it to B. So here, so this has been done. Now what C will going to do in message 1, now C attempts to connect to A claiming it is B with a challenge RB. Note that this is the same challenge offered it by B in message 2. So what the message 2 will be from A responds to the challenge with the encryption key EK of RB and a nonce of its own. So now what message 3 will going to do? So message 3 uses A response encryption key EK of RB to complete 3-message authentication protocol with B. So what as the attacker C accomplished here, C has successfully impersonated A and B, hence the message 3 was required to complete the authentication of C, posing it as A and to B. So that is what mutual authentication is of. So this is the corrected protocol where A will going to send its identity A to a B with a nonce A. So what B will going to do? B will going to encrypt this nonce which has been sent by A with an encryption key EK, and it will also send the encryption key with a nonce R which is of B, nonce of B. So what this third message A need to do, A will be decrypting the message what has been sent by B, and it will going to send only an RB to B which if the RB, whatever the message sent by A and whatever the message sent by RB, if it matches, then it will going to it will going to be an authenticated one. This is what the shared secret based authentication is. So next we're going to see asymmetric key based authentication. So what did it mean by asymmetric key based authentication? Here we assume that both A and B have a public key or private key pairs. So in the above figure, wait a minute, asymmetric key, yes. So here in this, what we will going to do, here in message 2, so here, what in asymmetric key, here A will going to send its identity with a nonce of R, with nonce R of A and A's certificate to B. So in message 2, the string obtained by concatenating the nonce of RA and RB is signed by B. Both the nonce and the signature are sent. So nonce RA is the challenge provided by A, RB is the challenge provided by B, and signed by A in response with a message 3. So this is what it is. So is this protocol a flawed? Is there any flaws in this protocol? There appears to be a flaw in which this protocol can be abused. So here what it will going to do, here message 1, A initiates the communication. So same way as the previous one, here A initiates a communication with C, sending a challenge RA. So sending a challenge RA. So message 1, C initiates a communication with B using the same nonce RA supplied by A. So message 2, in what the message 2 will be, so B will going to respond A's challenge and includes the challenge of its own RB. Here it is, RB. So what C will going to do in message 2, C will responds to A's challenge and uses B nonce, comma, nonce and the RB as this challenge to A. So in message 3, what it will going to do, A responds to C challenge here. A responds to C challenge, which was actually generated by B. So A does complete the mutual authentication protocol with C, and in message 4, C forwards A response to B. This is what the asymmetric key based authentication is. So if it is doing like this, what C will going to get, the C will going to get both A's information as well as the B's information. This is what the corrected protocol is of. So where A will going to send its identity A with its nonce A to B. So where B will going to send its nonce RB including to the previous message B, and what C will third message will going to contain. This third message will going to respond with a C's challenge and thus completes the mutual authentication with protocol C. So one solution to the problem in the sender is to include the identity of the recipient in all the messages signed by him. So if C tries to forward this message to B in later, will going to identify the C's identity that is included in the message. So B will going to realize that the message was intended for C, not for B. So this is what asymmetric key based authentication is. So next we're going to see authentication and key agreement. So in previous section, authentication was performed using operation involving a long-term shared secret or a private key. So here it will going to use combined mutual authentication key exchanges, that is uses a secret key cryptography and the public key cryptography. In both the figures, there is SA and SP are the contributions to the secret key A and B respectively. So there are freshly chosen. So this is what SA and SB. So SA and SP are the secret key generated respectively by A and B. So there are freshly chosen random number that are encrypted and sent to that. They cannot be eavesdropped upon. So there are encrypted messages 2 and 3 by a shared secret K. So they are encrypted in message 2 and 3 using the recipient's public key. So here what the A will going to do, A will going to send its identity A and along with the nonce RA to B. So what B will going to do, B will going to encrypt this by using its key of RA nonce which has been sent by A, and it will also encrypt the key RB, and SB is the secret key of B which has been shared by B. It will going to encrypt that. What 3 will going to do, third message will going to do, third message will going to decrypt, and it will going to get the it will going to obtain the nonce of RB, and it will going to share its secret key of A by encrypting it with K value K. So by using a public key cryptography, same here it is, it will going to share its identity A to B using its nonce RA and its A certificate, same as usual. Whatever the communication it was doing here, the same it will be done, but here it will be using the public keys. So here it was using K cryptography K, here it will going to use the public key PU. So this is what the authentication is of. So next we will going to use of timestamps. So what do you mean by this use of timestamps? So the use of nonce was introduced in the previous section as a means to prevent reply attack. Basically, each party generates a nonce which is used as a fresh challenge to other party. So the recipient is often expected to sign or encrypt the challenge using a secret known to only to the recipient or to the sender. So the idea here is the freshness of the nonce. So an alternative to nonce is a timestamp. So ideally, by securing stamping a message with a current time, you convince the receiving party of its freshness. So the figure shows the same. So here A is the identity of A and B is the identity of B. Here TA is the timestamp. At this particular time, I have sent this message. This is what the timestamp is of, and with a secret key shared by A, and it will going to be encrypted by using a public key PU and with certificate A. So, and it certificates A. So here in message 1, A inserts a timestamp TA inner message and signs it. And B, on receiving the message, check whether the timestamp is sufficiently recent and then verifies the signature. E increments the revised timestamp, inserts into his response message to A and signs the message. So here what it will going to do, the B will going to increment TA with TA plus 1, and it will going to send it to A. So this is what the mutual authentication using a timestamp is. Thank you guys. So we're going to continue next class. Thank you.